Good morning, good afternoon, and good evening, everyone. So it's been a while since I've done this again. Um, but basically, we're going to be doing exercises on linear algebra. And just to do a bit of review, so we've covered pretty much lines, the ideas of lines, what it means to be in the y mx plus b, those types of ideas. We've covered linear systems. Yeah, it's been a while since I've done this actually. So linear systems. So here is just basically different kinds of lines. Okay, this is a bit ugly, but something like this. X, X1, Y1 maybe. What, Y2. Yeah, something like this. Combinations of lines, right? And then we've covered how we can convert them to augmented matrices and how we get their spans if they're in some sort of span. And I think that's it, if I'm not mistaken. That's everything we've covered so far. Oh, and how we use, and then some linear algebra techniques like Gaussian elimination and all of those stuff. But we're going to get into them in a bit. Okay, so let's just hop right into it. Let's just go with an exercise here. Okay, right. So let me use my snipping tool, get the question. Right. So here it says that we want to determine if B, so B is a vector in this case, right? If we remember what the vector is from my previous calculus series, so that was about a month ago. And so we want to determine if B is in the span of the other given vectors. And what does it mean if B is in the span of other vectors? We say that, okay, maybe let's do something geometrically, right? So if you remember our 3D coordinate system, I think we called it X, Y, and Z. But now, since we're going into more high-level math, we're going to call it X sub 1, X sub 2, X sub 3. Now, the reason for this is we might be in more dimensions than just 2D or 3D. We could go ND. And so I want to consider that fact. Okay, and now what does it mean to be in a span? Let's say this A1, A sub 1, negative 1, 4, and 3 is, I don't know, it's that vector. Let's say that's A1. A2 is, let's say, this vector here. And so maybe a span would be something like this, that plane. Because if we kind of move the vectors around, think of it like a string. If we move these strings around and it's attached to the origin, we move it around, it's attached to the origin, it could go this way or it could go this way, right? And okay, this is a bit messy, but the idea here is we want to know if this B vector is within that span, is inside that area of, or inside that plane, right? That's what we want to know. And there's a mathematical notation for this, which I'm not going to go in depth into, but it should be pretty simple. And a definition of span, when we say that, so that was geometrically. Algebraically, it means it's a set of all linear combinations. Linear combinations of what? Of, in this case, A sub 1 and A sub 2. Now, we haven't covered this, but what exactly are linear combinations? Linear combinations are, I'm not gonna do, let's do it in a math way. So linear combinations, let's say we have those two vectors, a sub 1, a sub 2. And remember, scalars are basically real numbers. So scalars are real numbers. Let's just denote it as S sub 1, or no, not S sub 1. Let's do alpha. Alpha sub 1 is a scalar, alpha sub 2 is a scalar. They're both scalars. And the idea is that if we want a linear combination, we have to multiply a scalar to both vectors, and then we add them together. And that should give us a different vector, let's say W in this case. Right? And that vector W is a linear combination of a sub 1 and a sub 2. And W is a vector. And so in this case, we do a linear combination of these two vectors that we're given, which are a sub 1 and a sub 2. And that should give us D, which is -10, which has components -10, -8, and 7. Right? So let's actually now answer the question. Is B in the span of these two vectors a sub 1, a sub 2? If so, express B as a linear combination of the other vectors. So what we're going to do here is we're going to try to find two scalars. Let's do it alpha, right? We want to find two scalars. So we want two scalars. Let's do a alpha sub 1, alpha sub 2, such that, well, if we multiply these scalars to the corresponding vectors that we have, we will get this B vector in return. So in other words, we're trying to find a solution. So let's actually break it down. Alpha sub 1 times a sub 1 is, a sub 1 has components -1, 4, -3. Alpha sub 2 times a sub 2, which has these components, and these are equal to B, which has these components, right? And then we can keep going. Well, here we see this is actually a linear system, right? The linear system is -alpha 1 plus 2 alpha 2 is equal to -10. Then we have 4 alpha 1 plus 8 alpha 2, which is equal to -8. We have -3 alpha 1. So you get the idea, right? We're multiplying the scalar to each of the components of a given vector. And so the way I would solve this is not by doing that and then using substitution, because that's very, very slow. I would convert them to what we call an augmented matrix. So an augmented matrix is basically getting all of the coefficients in one spot from a linear system, right? Then here's our solution. So our B vector is here, and our A sub 1, A sub 2 are here. A sub 1, A sub 2, B, right? And then we're going to use this idea called Gaussian elimination, which is an algorithm used in many computers, but the teacher wants us to do it by hand, which is pretty annoying, but that's the way it is, right? We start by doing it by hand first, then we do it in a computer. So we want to use Gaussian elimination to convert it to what we call echelon form. Now, echelon form, when you see planes, right? You see these planes, they all go like this. They have this some sort of formation. This is like an L-shaped formation. Another formation that they do is the slanted thing, right? Imagine these are planes, these aren't circles. And so the idea is that we want this thing to be in row echelon form. And what that means is, let's say we have numbers here. In this case, we want these specific ones. So the dots are numbers. We want these specific positions in the augmented matrix to be 0 so that we can use what we call back substitution. And if we use back substitution, we're going to get solutions for alpha 1 and alpha 2. Right? So I'm going to show that in a bit what exactly that is. But for now, we need to use some Gaussian elimination techniques, and we have 3 of them, right? We can switch rows. We can multiply a row by some scalar, and we can also add and subtract one row from the other. So let's quickly do that. Let's try to get rid of this -3 down here. So what would I do? I would multiply, so here you can go a lot of ways. I would multiply -3 to this row 1. So this is the annotation for it. We call this row 1, row 2, row 3, and then we do some simple arithmetic operations to it. So I multiply -3 to row 1, add that to row 3, put that in row 3. So let's just go for it. -3 times -1 is 3. -3 times 2 is -6. -10 times -3 is 30. So we keep doing that. This stays the same. This one, okay, now we do the adding. 3 minus 3 is 0. Boom, we got that. -6 plus -7, that's -13, I believe. Right? And then 30 plus 7 is 37. And then the good thing about this is I can reset the thing I scaled because it's basically the same thing. Right? Okay, then now I keep going. So I want to get rid of this 4 in the second row. How do I do that? I could maybe multiply -4, or in this case, actually, I'll multiply 4. And then I can subtract row 2 from it. So I would say row 2 minus. Ooh, that's weird. -4 of row 1. And then we put that in row 2. So I multiply -4 to row 1 first, and then row 2 minus row 1. Right? So this will give me what? This will give me 4. Actually, wait. Oops, it's not -4. Because that would make it positive. There. Should just be a positive 4. So this becomes -4, right? So I multiply everything by 4, right? So 2 times 4, 8. -10 times 4, -40. This stays, oops, my bad. Row 3 stays the same. Row 2, on the other hand, we subtract it to what row 1 is now. Or shoot, we actually add it. My bad. 4 minus 4. 4 plus -4 is 0. 8 plus 8 is 16. And then -8 plus -40 is -48. Then we can reset row 1 because we just scaled it. And then from here, now I want to get rid of this, make that 0. How do I do that? Well, okay. I could scale this 16, make it 13. Now, there has to be a way to do that, right? And the way to do that is we have to multiply something. So some value, let's call it B, or no, no, let's call it D, which is equal to 13. So that means when I divide this thing, D should be 13 over 16. So that means D is 13 over 16. That way when we cancel, it's 13 equals 13, right? So I have to multiply 13 over 16 here so that I can get 13. So I multiply 13 over 16 to row 2, right? And then I add it to row 3, put that in row 3. There we go. So I ignore row 1. I scale this. So 0 times 13 over 16 is 0. This becomes 13. Now this, negative 48 times 13 over 16. It's a bit weird, but I could scale it down, right? I could divide this by 4, divide this by 4. This would give me 12, I think. I could keep going. This gives me 1, this gives me 3. Negative 3 times 13. Using my calculator, we get 39. Negative 39. I hope that's right. You guys help me check that. And then here is where the magic happens. 0 plus 0. 0, 13 plus negative 13, 0. Negative 48, oh no, negative 39 plus 37 is negative 2. And the good thing is we can scale this. Or we don't. Doesn't matter. Right. Ooh, we could actually... So instead of this, we could divide this by something to make it easier for us to solve. What would that be? I could divide a 4. This becomes 4. Could divide this by 4. This becomes negative 12. I could divide it again. This becomes 1. 4 divided by 4 is 1. This becomes negative 3. And I think that's the simplest row echelon form we can get, right? Because we now have the 3 zeros that I'm looking for. And now we can convert this back to a linear system, and it's way easier. And here we can actually see, and this is a bit funny, 0 is equal to negative 2. So this means this whole thing that we did is, well, not useless, but it means that there is no solution, right? Otherwise, this would have been fine. We had here, what was this? We had here alpha 2 is equal to negative 3. Then here we had negative alpha 1 plus 2 alpha 2 equals negative 10. But we cannot solve for this last one. And so what's the answer to our question? And we're going to check if this is right. Is B in the span? No. That means B is not in the span. And then we're going to put D in here for both of these guys. Let's see if I got that. If I didn't, then means I don't know the topic well. But should be D and E. And we got it. It's correct. Let me share. Can I share this? There we go. I hope I'm sharing the right screen. So the reason why it's not in the span, and therefore we cannot, there is no linear combination. No, there is no linear combination, therefore it's not in the span. That's the way to think about it, right? Okay, let's move on to question 2. And I think we can do this this. Oh no, we have to do some math here. But let's see. Right, so funny enough, that was a lot of math for just a simple question like that. It is. An easier way to do it? Well, ask GPT, which I might do if I don't know how to solve this thing. Okay, let's look at question 2 here. So question 2 is asking, or it's asking us to determine if the columns, so when we say columns, we're talking about these guys. That's how we look at them. We want to determine if these particular columns span R2. And what that is saying is geometrically, say we have our 3D space. Let's just call it XYZ for now, because that's what we're used to in Calc 3. And what it's saying is that it belongs to this area, basically the XY plane, how we used to call it. All the vectors are there. Now, is that true? From the looks of it, I think yes, intuitively, just because there are two components in each column. And that's why that's my guess. But is there a mathematical way to prove this type of thing? Well, there is. We could do since a span is a set of all linear combinations, then we want to find linear combinations of these things. But actually, I don't think we need to, just funny. Let me see. Yeah, I'm asking AI. Okay. Oh, so it messed it up. That's funny. Put this up here. Yeah, it messed up the positioning of the numbers. I wouldn't be surprised. It's AI. Right, so it's a 2 by 3 matrix. The columns span R2 if we can form any vector X, Y, so linear combination of any. Okay. Check if the columns are linearly independent and rank of A is 2. Oh, we could check if they are linearly independent. But we didn't really discuss that yet, so I'm not gonna use that idea. I would rather just, here's what I'm gonna do. What? You can try using 2 columns first. Actually, I'll just ask AI to not use linear independence. Right, so what we want to do is separate these into vectors. Call it v1, v2, v3. That's the first thing I would think of doing. We're gonna say let this be this. So these are vectors, column vectors to be specific. Oh, I didn't put the equals. That's funny. Right, so these are vectors. And we're going to see if they span in R2, right? So to check if they span in R2, we get scalars. A sub 1, 2, and 3. And we basically solve this thing, right? So we get their linear combination. Okay, so how I would do this, same idea as before. Right? And then this would equal, so alpha 1 is 2, 6, or multiplied by v sub 1, alpha 2 multiplied by v sub 2, alpha 3 multiplied by v sub 3. And then we could convert them into something. Oh, so now the thing is we can't convert them into an augmented matrix, right? So what's going to be our solution? Here we maybe let's do B. Let's do B sub 1 and B sub 2. Let's say this is part of R2. If it's part of R2, then that means the span of this is part of R2. So we say that the thing that we're doing here, the vector equation, is equal to this thing. We're going to check if there is such a solution. So I would convert them to an augmented matrix here. Right? And then I would convert them to a row echelon. Now I can see here we have a free variable actually. Right, so you can multiply this by, you can multiply this by 3. This is really a simple one. Subtract it to R2, put in R2. It's that simple. 6 minus 6, 0. Right? 3, 0, 3b1. This becomes 3, 3 minus negative 3, 6. 0 minus, so positive 1, 0 minus negative 1, 3b1 minus 3b2. Then I can just repeat. Rinse, repeat. No, I'm kidding, not rinse, repeat. I could reset this to the way it was. And there we have it. We have it in row echelon. But here we have a free variable, which is alpha sub 3. That's our free variable. We're going to let that be S1. So we assign it as S1, where we say these are free variables. They can be anything. Since This is a free variable. Right. Now I think we can solve this using back substitution. So what I would do is 6 alpha sub 2 plus alpha sub 3, which we say that's S1. S1 is 3b1 minus b2. So that's the first thing that we can see from here. I'm starting from the lowest row. Right? Now we basically isolate this, we get alpha sub 2. So alpha sub 2, or let's do it step by step. Right. Now we have 1/2 b1 minus b over 2 over 6, or minus 1/6 of b sub 2, then 1/6 of s sub 1. And that's one of these solutions. And then we go ahead and look at the first row, which tells us, put check mark here, 2 alpha sub 1 plus alpha sub 2. Now alpha sub 2 is this thing, this whole mess is equal to b1. I didn't include alpha 3 anymore because it's 0, right? And so here we isolate everything. We solve for alpha sub 1. And so here we get a half, right? So here I would divide everything by 2. I think this was 12. There we go. And there's the other one. So what was the question? The question was, do the columns span? We have a free variable. Right? But the thing is, we can find these scalars. Right? And so if we can find these scalars, these alpha sub 1, alpha sub 2, alpha sub 3, then we know it spans R2. If there is no solution to our linear combination, then we probably can't. Just like the previous example, but here we can. Right? Okay. So I'm gonna say yes. Column span, and that's correct. So the reasoning behind it is we didn't really end up with no solutions or anything, but since we can find these scalars, alpha sub 1, alpha sub 2, alpha sub 3, all they're real numbers, column span in R3. Did I say R3? R2, my bad. So yes. Okay. So it's a very theoretical thing, but yeah, we're gonna get through it. Okay, let's go through question 3 real quick. Now, question 3 is telling us yes or no. Uh-oh. The weird thing is I can't really see what I'm looking at. Right. So here for the matrix A given, so this is a matrix. Let's determine if the system AX equals B has a solution for all choices of B. Okay. But we have this assumption that X and B have the appropriate number of components. What does that mean? Well, it means that, okay, maybe this is just an assumption of mine, but X is probably a vector, right? That has two components, and B is the same thing. I think that's what it means. So to write it out mathematically, X and B probably have two components, similar to A, because A is a 2 by 2, right? But let's see. So does it have a solution? Again, what I would do is I would just do a linear combination, right? But is there some sort of contradiction here? Let's see. Let's find out. Okay, I asked AI just to be sure. Okay, it's talking about all these invertible stuff that I haven't learned yet. So here I would just write it as a linear combination, right? And every check of the column spans R2. So it's very, very similar to the thing that we did. I'm trying to think of a way. Okay, so bottom line is if B or let's say in this case, if for every B that belongs in R2, we can find scalars, and these scalars are, okay, this time let's call it x sub 1 and x sub 2. Then from our previous thing here, the columns can span R2, right? Because the thing about this actually is everything here, when we're in 2D space, spans in all of 2D space. So really, geometrically, what this looks like is if we have two vectors, we find their linear combination. That could be one, that could be one, that could be one, that could be one. It's all of R2. That's what that's saying. But in 3D, it's a bit different. Some can span in R3, some cannot. And that depends, right? Because when we say span, it's the set of all linear combinations given a certain number of vectors, right? But if we have, let's say, a number of vectors that have two components, then they definitely span in R2. So in this case, even without doing it, this is a yes. The reason is these are two components, and so we can definitely find scalars for them. So like this, we can find something like this. And so their columns span, right? And if they span, so here's where the if columns span in R2, then what we're saying is that the system has a solution for all B, right? So if there is a linear combination that produces any B, then we basically fulfilled the condition that was being asked in the problem, right? Since it's all choices of B, and that just depends on the linear combinations that we have. So this is basically a yes. We don't have to go through it. Let me just check, see if we got it. I would say that's a yes. Okay, we got it. If it was a no, I would have been worried. But hey, it's not a no. Okay, moving on. Question number 4. And this is asking us to find values of h. So I wonder what h is going to be. Is it a scalar? Is it a vector? Actually, I'm just going to put it here. Let's see. So you want to find values of h such that the vectors a sub 1 to 3 span R3. Oh, so h here is a scalar. It's actually a component of a sub 2, the vector a sub 2. And so what is h? We have two slots here. I don't know if this means 2 digits or something else. But again, if we want to say that this thing spans in R3, we want to find the set of linear combinations, and so we want to find linear combinations for these 3 vectors, right? That's the whole idea here. So to check if such vectors span in some particular R2 or Rn, then we get their corresponding scalars, or we don't get corresponding, oh no, yeah, we do get corresponding scalars and their linear combination to see if, well, this thing works, right? But here it's asking us, it doesn't span in R2, it spans in R3. And from the looks of it, I would say yes, this will span, because we have 3 components for each vector. If we had more components, then there's this possibility that it doesn't span. Unless that next component is a 0, it will span. Okay, let's see. Oh, we're asked to find all values of h, and it's giving us a clue that the h has two values. Oh, wait a minute. Oh, it's asking for a set. H equals greater than equal to H not equal. Okay, sure. Let's just try this out first, yeah? Let's get their linear combinations. Says here it spans R3. So the way we did this was we just, well, actually, this is a bit different. Because we don't have like an equal B or something. Let's see. See, that's why I use AI, because I don't really know. It's asking us to compute a determinant, which is weird. Let's see. Okay, so it's definitely gonna tell us what it is. Okay, saying H should not be 4. But let's try to solve that, shall we? Let's get the linear combinations of these guys. Okay, so A sub 1, A1, A sub 2, A2. Or let me say A sub 1, A1. Alpha sub 1, A1, alpha sub 2, A2, alpha sub 3. A3 is equal to some B vector, right? And so let's expand. So alpha sub 1 times the A1 vector, 2, 4, 5. So basically similar to what we've been doing. Here we put the H, 8 and 10, 1, 2, and 6. Now my B vector, let's just do subs. So B sub 1, B sub 2, and 3. Cool. Now let's convert them to an augmented matrix. Now the thing about me, I could have just converted them directly, and I don't know why I didn't do that. Now let's convert it to row echelon form so that we can use back substitution. Right, so let's get rid of this 5, make it 0. How do we do it? Well, we can multiply 5 halves to 2, right? Row 1. Then we subtract it to row 3, put that in row 3. So that's what I was thinking. This would be 0. This would be 5. This would be 5 halves h. 5 halves h minus 10. This would be 5 halves minus 6. I wonder what that is. 6, 2, 12. 5 minus 12. Minus 6. 12 over 2. Negative 7 halves. We have 5 half b1. 5 half, oh shoot, not 5 half b1. Oh yeah, you're right. 5 half b1 minus b3. And then we keep row 2 as it is. Right, I keep going. Now, so now let's do 4. We multiply 5 by 4/5, maybe? To get this row 1 to 4. And we subtract that to row 2. We assign that to row 2. So now we have 2 zeros here. This becomes a 4. Oops, my bad. I forgot to reset this whole thing. Because I could reset it. So I have 2H1, B1. And then this could be a 4. So I could actually just multiply this by 2. I don't have to like, yeah, and I could still subtract it. We have 2H here. We have, what's this, 2? 1 times 2, 2. B1, 2B1. Right, we just subtract everything to row 2. So we have 4 minus 4, 2H minus 8. So here, funny enough, we could divide these. Divide that. Now we don't want to do that. 2 minus 2 is a 0. 2B1 minus B2. Right. Let me just copy these things. We have 5/2 H minus 10. Negative 7/2. 5/2 B1. Oh, what is that? Minus B3. Right. And this is it. Now you can just reset this R1 to what it used to be. 2H1 B1. And lastly, let's get this thing to 0. How do we do that? We want, so I want to multiply this by some k value. I'm just going to use k. We want to make this, how do we make this to 0? 10 minus 5/2 H. Right, and then we just add this thing. That should be 0. And so the way to get this k is, it's actually, funny enough, pretty simple, but it's just this. No, I'm kidding, it's not that simple. Is there a way we could simplify maybe? I could divide everything by a 2. This would be a 5 minus 5H. Divide this by a 2, this is H minus 4. Cancel this out. I could do 5, 1 minus H, H minus 4. So that's what I'm going to multiply it with, which is a bit weird and complicated, but this should work. I multiply this to row 2. That should give me 10 minus 5/2 H. Then I add it to row 3. Then pass it to row 3. That should give me it. Let's see. Okay, and then from there, nothing to bother with row 1. Let's keep it as it is. This is 0, this is 0. This is 0. Right? Because this gives me 10 minus 5 half h. Add it. This is 0. So this would give me, oh, this is a long one. Negative b, or negative 7 half. 0 times this is just 0. Same thing. Yeah, so we have 0 minus 7 halves. And then, oh, so this thing times this thing. Geez. And then I add that to this thing. Right? So that whole thing, hell no, I'm not simplifying that. But the funny thing is I can kind of see it. But here, 2b1, 5, 1 minus h, divided by h minus 4, plus 5 half, b1, minus b3. And from there, what shouldn't h be? So here, looking at row 3, h should not be 4, since that would be undefined. So I think that's the answer. H shouldn't be 4, else that would be 0. Right? If that's wrong, I don't know. We got it. Nice. Phew. Okay. Good stuff. We got it. Now question 5. Let's see what this is. Oh, I got my name. Okay, let me... Okay, this is the last one for the day, and I'm going to take a break. Right. Question 5 is asking, for the matrix A given, determine if the system has... Oh, didn't we just do this before? Right, we did this before, but here is our property, right? So there has to be a way to just go around this without looking at it. So here again, we say that we assume x and b have appropriate number of components. So we say x and b are both vectors in R3. Reason it's in R3 is because A is a 3x3 matrix. Now the question we're asking is if this system AX equals B has a solution for all choices of B. So we can just use this explanation and just tweak it. But I think the answer would be yes. Right? So if for ever B in R3, we can find some scalars going all the way up to 3, x sub 3. and the real numbers, and then the columns, all of these columns span in R3, which I think it does. I don't see a reason why it wouldn't. If the columns then span in R3, then the system has a solution for all B. So I would say that's a yes. And it's not. Why is it not? Of course it's going to be a no, because it's math. Why is it a no? Does it have a solution for all? So we can write a linear combination. I'm just reading what AI is telling me. Apparently it doesn't. The system must be consistent. What does it mean for a system to be consistent? It means it has at least one solution. Okay, actually, let's just talk about linear independence and dependence. And I think that should be easier than just going through this, right? So let's just go through it. Here's what it means, basically. If columns are linearly independent, linearly dependent, not independent, then we basically have a non-trivial. When we say non-trivial, it's not that significant because it's super obvious. You have a non-trivial combination that equals 0. Now, what does that mean? Say we have scalars, right? C1, C2, C3. Where we say that C1, C2, and C3 are 0 and they're real numbers, right? But if there is another solution that is trivial, then it's linearly independent. Oh, wait, there is a non-trivial, if there is, whoops, my bad. Non-trivial means a hidden solution. It's independent. Independent. There is a trivial. When we say trivial, it's super obvious. I reversed it. But there's a trivial or an easy solution that's basically 0. But, so I didn't talk about this too much here in this class. I talked about it in an applied linear algebra class, but we say they are linearly dependent if there is a non-trivial or a not so easy to find solution or combination. An example of linearly independent is the standard basis vectors, right? And that is the ijk vector that we talked about in our calculus class. Why is that? If we add those vectors together, we get 1, 1, 1. And so if we add scalars to them, say let's add alpha 1, alpha 2, alpha 3. The moment we add these guys, well, then we have alpha 1, alpha 2, alpha 3, right? And they're equal to 0. So we say alpha 1 is equal to 2, equal to 3, equal to 0. Okay, here in this case we used C, but here we used alpha. Same thing, it doesn't matter. But the idea is that that's what it means to be linearly independent and dependent. Right, so what does that mean? We're saying that if columns are linearly dependent, meaning there is a hidden solution or a non-trivial combination, they do not span R3. And if they don't span R3, right, then the system AX equals B does not have a solution for all B. It only has a solution for B in the span of the columns. So we say AX equals B does not have a solution for all B. It only has a solution specifically for the B's in the span of the columns. That's what that means. Now, there is a mathematical way to prove this. I might go through it. It's a bit weird though. Or wait, actually, I think we can go through it. Let's just go through it. So we have these vectors, right? Let's see. Let's go ahead and go immediately to the augmented matrix. Negative 3, 1, 5. Shoot, I forgot the other ones. 2, negative 1, negative 4. 1, negative 1, 3. Negative 3 is equal to some B, B1, B2, B3, right? We can convert them to echelon form, all of that stuff. And if we do that, I don't want to go through the hassle of doing it. I just want to let the computer do this for me, or specifically AI, to just convert it to a Gaussian elimination, which would give me something. I want to do all of those steps again, but we'll see. Right. Did it get everything correctly though? Okay, it did. Great. So we should have this thing. 1, -1, -1, B2. Then we have 0, -1 and 2, -2. Then we have 0, 0, 0. B1 plus 3B2. B1 plus B3 plus 2, or no, not plus, minus 2 B2. And now this, I'm not saying this doesn't have a solution. I think it has. So the last row reads as this: 0 equals B1 plus B3 minus 2B2. Now here's where the issue happens, right? The reason why it doesn't work, because B3 is 2B2 minus B1. And so if B satisfies B3 equals 2B2 minus B1, then the system has solutions. If B does not satisfy that relation, the system is inconsistent, so no solution. And so that's why AX equals B does not have a solution for all choices of B. Right? So I'm just going to write that out. If B, this B vector satisfies this thing, system has solutions. So this is the algebraic way of doing it. But if B does not satisfy that relation or equation, doesn't really matter what you call it, system is inconsistent, or it means it doesn't have a solution. So AX equals B does not have a solution for all choices of B. It has to satisfy this thing. Okay, so that's that for these skills problems. I hope you guys enjoyed. I hope you learned a lot. I certainly did. And sorry it's been a while since I have posted. Autumn quarter is super busy here at UW. So yeah, I hope you guys learned a lot, at least from this. It's just a brief glimpse of linear algebra. I don't know when I'm going to be able to post consistently again. It was the summer that time, so it was definitely easier. But in this case, there's a lot of activities going on, and I'm just trying to find the time to do it. So yeah, I hope you guys enjoyed and learned something at least from this video, and I'll see you guys in the next one, whenever that may be.